We left off, Chapter 5, Section 2, Compound Interest. We talk about effective rate, and actually present value is the last thing in the section. So if $1 is deposited at 4% compounded quarterly, you can find out the compound amount is 1.0406, an increase of 4.06% over the original amount. So the actual increase of 4.06 is a little bit higher than that stated rate of 4%. Okay, so we have these two numbers. One is the nominal or stated rate of interest, okay, and we have this other one, this higher one, is the effective rate. Okay, so this actually is called the APR, the annual percentage rate. So you actually do see the effective rate occasionally, but yeah. All right, so effective rate, you have this formula right here. The effective rate equals 1 plus R over M to the M minus 1. It actually looks pretty similar to our previous equation with compound interest. Okay, this is what we're going to use for the next couple of these. All right, let's jump into our example. Find the effective rate corresponding to a stated rate of 6% compounded semi-annually. That means M equals 2. So that formula, the effective rate, which I'm going to write this little subscript of an E so to differentiate between the two. Effective rate is 1 plus R 0.06 over M to the M minus 1. And so the effective rate here is actually 6.09%. Okay, now what this is actually showing you is the annual interest rate. Ignoring the compound and semi-annual, it takes that into account to show how much you're actually paying in that year. That's really what the effective rate really comes down to. And that's right. This next problem is where it's going to be useful. Okay, Joe needs to borrow some money. His neighborhood bank charges 8% interest compounded semi-annually. A downtown bank charges 7.9% interest compounded monthly. At which bank will Joe pay the lesser amount of interest? So I'm actually going to write this two ways. We've got our neighborhood bank and we have our downtown bank. We need to differentiate between the two of these. Okay, so the neighborhood bank has a rate of 8%. Okay, and it's semi-annually, so M equals 2. The downtown bank, however, has a rate of 7.9%, and it's compounded monthly, so M equals 12. So at first glance, okay, you might go, downtown bank is obviously the better choice. Their billboards look nicer, and they have a lower percent of interest. But they don't charge interest as much. They charge it semi-annually. So, well, they charge interest more often than the neighborhood bank. Okay, they only charge interest twice a year. They charge it 12. So we'll have to see how this works out. So the effective rate for the neighborhood bank is going to be 1 plus 0.08 over 2 semi-annually to the 2 minus 1. So that rate actually comes out to be 8.16%. Okay. Well, right now it's looking worse, a lot worse than downtown bank, but let's work them out. 1 plus 0.079 divided by 12, and this 12 to the 12 minus 1. And that turns out to be 8.192%. So which one's going to charge him the lesser amount of interest? Well, pretty clearly it's going to be the neighborhood bank. See right there. Okay, so if he's really, when it really comes down to it, he better go to the neighborhood bank instead of the downtown bank because their billboards are nicer, but you know what? Less interest over here. So neighborhood bank. That's my actual answer since it asks which one. Next example, 11. Find the effective rate for an account that pays 2.7% compounded monthly. So our effective rate equals 1 plus our rate 0.027 divided by monthly M equals 12 parentheses to the 12 and then down here minus 1. So the effective rate here, when you work that out, you should get 2.734%. By the way, this is always just a little bit higher than the stated rate. It's kind of a fact. When compounding comes into effect, you pay more interest, or really a higher annual rate. All right, that's the end of effective rate. So we're going to start present value. Present value is going back to compound interest. Okay, so Rachel Reeve must pay a lump sum of $6,000 in 5 years. So 5 years is our time, and I might be tempted to say that's our deposit amount, but it says in 5 years. This is a future amount. Future amount is our accumulated amount, so A. What amount deposited today at 6.2% compounded annually, M equals 1, will amount to $6,000 in 5 years? So what we're looking for actually is A, or is P. We want to know the amount that you could put in to get $6,000. All right, so let's just start out with the original equation we've got. P equals, that's not the right one, A equals P times 1, P times 1 plus R over M to the M times T. But we really need to solve for, we really want P out of this, right? So we're going to end up having to divide and solve some here. All right, so we could take 6,000, that's our A value, equals P times 1 plus 0.062 over M, which is 1, to the 1 times 5. All right, so simplifying this a little bit, stuff on the inside, we actually get something close to 1.35. Now again, use the exact value in your calculator. Okay, don't just round it. And then we'll divide by 1.35. Right, so P, and I say divide by that. Divide by the exact amount, and I get $4,441.49. Okay, so if you deposited $4,441.49 into an account set up here, you should get $6,000 in 5 years. All right, so there is actually a single formula that is really useful for this. Okay, it's basically the rearranged form of this guy right here. Okay, so instead of doing all this and solving and dividing, you can just divide by this quantity over here. Okay, so yeah, it started out as A equals P times 1 plus, and I'm going to go ahead and write it the way they have, I to the N, divide by this quantity right here, put it down here, and you have, voila, you have the same equation right there. So there are two ways you can see it, but really I kind of prefer this one. So this one says find the present value. That means we're looking for P. So we want this equation, this is the present value equation, of $16,000 accumulated amount in 9 years time if money can be deposited at 6% compounded semi-annually, 2 times a year. So we want to find P. So we're going to take A, 16,000, divided by 1 plus R over M, 0.06, semi-annually divided by 2, to the 2 times 9. Now make sure you're careful about your parentheses and whatnot and what's on top and bottom of that fraction. But in the end, you should get $9,398.31. Okay. I think I said this at the beginning of the first section, but the big thing with this is knowing which formula to use when. So present value, we want P equals. Okay. Most of these equations are going to be given, okay, on a fact sheet at some point. So you don't have to memorize these formulas, but it's a good idea to know how to use one and which one to use. Okay. Find the present value of $10,000. So we want to find P. That is our A. In 7 years, T. If money can be deposited at 4.25% compounded quarterly. It's going to be almost exactly the same. P equals 10,000. Big fraction. 1 plus R, 0.0425 over M, which is 4, all to the 4 times 7. So if we work that out, we should get $7,438.39. Always rounding. right, example 15 and 16, we're actually going to need a little bit of our technology for this one. So example 15 says, suppose that $2,450 is deposited at 5.25%. Okay, so that's our rate, compounded quarterly. M equals 4, and 2450 was our deposited amount, our P, until it reaches at least $10,000. It's our accumulated amount. How much time is required? All right, now I think I want to actually use our TVM. I'm pretty sure we can do that. Yeah, we can certainly do that. Our TVM, so we're going to do N equals number of payments, I as a percent, equals future value, wrong one, future value. Okay, we've got payment, present value, yes, present value, payments per year, and compounding periods per year. For us, these two are always going to be the same. Okay. Now, it's 4 times a year, so this is M. That's both going to be 4. The present value is 2450. All right, let's see. Payments, it's going to be 0 for us. Future value is $10,000. Actually, scratch that. This doesn't work because we can't find in. We don't have enough information really. So sorry, nice try. Okay, so we're going to have to actually do what we did earlier. We have our equation 2450. Okay, times 1 plus R 0.0525 over 4 to the 4 times time. We want to know when that is $10,000. So we're actually going to have to do another graph. Okay, so I'm going to go back to my Inspire. Alright, so here we are. 2 equations. Let's see, tab. I'm going to change that first equation to, it was actually really close. It had the same interest rate and everything. Alright, so let's see, P times 1 plus, there's our interest rate, over 4 to the 4x. All right, and we want to win $10,000, which if we go down, $10,000 already. Okay, so everything is all set for us to use this. I'm going to need the menu. Okay, so we want to know where they intersect, which we can actually see that there. So menu, analyze graph, intersection. It's between there and there. Intersection is at 27. 27. So that means that our time is 27. 27 years. On the dot. Okay. All right. Last example, number 16. Suppose the general level of inflation in the economy averages 8% per year. Okay, I have a rate. Find the number of years, so we want to know T. It would take for the overall level of prices to double. Now, it may make you feel a little bit uneasy that we don't have our future value or present value. So here's what we're going to do. We want to know when the prices double. So pick your favorite number. I'm going to just use 1. Okay, let's say the present value is $1. Okay, in the future, how much is it worth if it doubles? It's worth 2. Okay, you could have done it with 2 and 4 and it'd still work. Okay, so we're going to actually use this information right here, our present value, our future value, which present value is P, and our future value is A. So we have A, P, and R, and we want to find T. And it actually says per year, so it's kind of assumed that M is going to be 1. So 2 equals 1 times 1 plus R over M, 0.08 divided by 1 to the 1 times T. Well, this is actually just like the last problem we did, isn't it? We just have 2 different equations. Okay, so we want to know when that, okay, oh, wrong button, handled side screen. Okay, So we want to know when, and I'm going to actually do tab, delete that whole equation, 2450, so it's 2 times 1 plus fraction 0.08 over 1 to the 1 times x. And we want to know when it's going to be 2. We want to know when these two intersect. Now, I need to redo my window, so I'm going to say menu, window, zoom, standard. Alright, so they actually intersect right in here. So we don't know when that's 2. So let's see here. Menu, analyze graph, intersection, 0, 2. Oh, I made a mistake there. This equation is not right. Change that to 1. Alright, there we go. Now, menu, analyze graph, intersection between here and there. And let me move that out of the way. 9.01. Okay, so our time is 9.01 years. Okay, and that brings us to the end of this section, I believe. Sure does. So that's the end of section 2.